Okay, to continue. Apologies for the people who dialed in. You missed a lot of jokes. Okay. So, uh, so again, with compile time, it's not costly. I mean, it's running on a developer machine. There's no extra environment, everything, and it's you kind of avoid the risk aversion bit, right? Once you have tests, things compile and push it. There are ways to make sure it's going to work. Okay, and and the deal is a lot of languages, especially TypeScript, okay, has a really good type system. And the whole idea is, that's the feature of the compiler. That's the best feature of the compiler you need to use. It's like a weapon, and you can actually use it to the max to make sure your systems don't fail when you develop, right? So use it, okay? So we're going to talk about that, okay? How we're going to solve issues with compile time. But in order to do that, there's one more important thing to do, and that is monorepos. And I'm going to briefly touch upon this. It's another whole topic altogether, okay? So in order to make your services, I mean, the things that I talked about, to work on compile time, you also need to move to use monorepos. And what I mean by monorepos is, typically in teams, when they start services, there'll be something like, 3 or 4 services distributed across different repositories and all of that. And then one repository publishes a package, the other one consumes it and all. This is not bound to work. If you want to check everything at compile time, they need to be in a single repository. Okay, so the first thing you need to do is move all your services into a single repository. Convince your team or whoever teams you're working with, okay, to commit, to commit to one repository. Okay. Now, once you have this in TypeScript projects, all the package managers has a feature called workspaces, where you have the root package.json. You can specify what your projects are, and then in any of the projects, like the bar service, okay, the bar word is a bit, but that's a foo bar is something that is used. Okay, there's no bar service here. You don't get free drinks. Okay, so you have the package.json, the bar service, depend on, let's say, the greet service. Okay, so this makes sure that when bar service is compiled, it's first going to compile the greet service, and then if there are any issues, it's going to be caught in the greet service. I mean, in the bar service. Okay, so like I mentioned, the bar service and the greet service. So once we have that, now we go on to the options. The first option is using OpenAPI, not to be confused with OpenAI. There's just one letter difference. Okay, I might say OpenAI, but I mean OpenAPI. Okay, so the first option is using OpenAPI. Okay, and I think many of the people are familiar with OpenAPI. It's kind of a spec for specifying how your API should be. Okay, so you start with the definition saying, okay, the path's greet, and there's a get, and that does that. Then you have a request, okay, and then you have a response, and there's a definition. Now I had to trim out a lot of information just to fit it into the slide. Okay, so OpenAPI is a very verbose specification for just that one greet API. There were at least like 3 pages of YAML configuration that I had to write. So these are the significant bits, like the schema and all is missing over that. Okay, so that's one option. So the idea is you have your code for serving your REST API. Then you write this OpenAPI specification. Okay, and then you use a tool called the OpenAPI TypeScript to parse the YAML and generate types out of the schema, a TypeScript type file. Okay. Now, once you do that, you can. So in greet service, you write what the schema should be, and in your bar service, you can import the schema. Okay. And then you kind of use the imported parts from that schema to create a client, a type-safe client. And then you kind of access it. So if you look at the code over here, the final bit of code over there. I have backup because I don't have a pointer. So here, so you see this is going to be auto-completed for you by the API because you imported it from paths, okay? And this is also, a type safe saying that, okay, this path has this parameter over there. So you kind of get that guarantee and type safety when you do this with OpenAPI. Again, some pros and cons, okay? OpenAPI has multi-language support. So and it's flexible. You can keep your API definition file different from your kind of service. So there's some flexibility in defining how things are. It's not embedded in how you write your service. Okay, it's a fairly open standard, very verbose one at that, unfortunately. And there is good tool support. There are a lot of tools that will allow you to parse the YAML and visualize it or publish it as a spec to the world. But again, cons, it's very verbose. There's a lot of boilerplate code for parsing and understanding OpenAPI. And it's not exactly real time. You need to parse whenever there are any changes, you need to update the YAML. And then the build process has to generate the schema and then refer. Only then you catch the issue. So it's how good you are at updating the files that makes it successful. Okay. So we still do bike shedding. We still haven't eliminated the problem of how it should be, what name it should be, what code it should be. So that problem is still there. So I mean, it is one option if your team is not convinced about anything else, but I think we need to twist and think about this problem quite differently. Okay, we need to stop thinking it's a controversial statement. We need to stop using REST and JSON. Okay, and think of it as RPCs, remote procedure calls, right? And what's the best thing? How do developers think? Right, they write a function which is greet, and there's a name, and it returns a message, right? Because we're so used to writing APIs in REST and all, we think in terms of request and response and this, that, and getting that, and that code kind of gets completely embedded in our code base, and it kind of pollutes it and make it only worth, an HTTP kind of a thing. So, I mean, what the best case scenario is, we have a function, it returns a message. Okay. Now we can choose to expose this function over HTTP. So think of that as a transport for this function. But developers must be getting close to writing functions. Okay. So, and then there's a client that can call this function, know exactly the parameters that function needs, and invoke it, right? So the good part is it is type safe. There is type safety. You know exactly what the parameters are, what the name of the function, and all of that. There's not much boilerplate code. You don't have to write any serialization, deserialization stuff. It is idiomatic. For example, if you want to throw an error, just throw an error, right? Don't throw an HTTP error or set a response, to do that, or throw an error as a JSON and not set 200 as the status. Okay, anyway, that's another discussion altogether. And then there's lesser byte shedding. Okay, at least it's minimized. I mean, people will still argue about the name of the function, but the status codes and how it should be, it's kind of minimized. Okay, so there are a lot of options right now to do this. A lot of tools to do this. Okay, first of that is gRPC. Now, gRPC is kind of battle tested. It's a very popular framework. And how it works is it uses protobuf, which is a binary protocol instead of JSON to transfer the data. Okay. Then it uses code generation to generate stubs for the protocol. Okay, and by code generation I mean there's a protofile which is kind of a schema definition of your API, where you say, hey, this is the service that I have. This is the service that I have. This is the name of the method. It's an RPC greet method. This is the request. This is the response. Okay. Then you say the request has a name and the response has a message. That's it. That's the protofile that we have. Okay. It is, yeah. I mean, that there itself, there's a win. Okay. There's a schema definition language, which is much less verbose than OpenAPI YAMLs. Okay. Now, once you have this definition, you compile stubs from this definition, which will generate files to work with this service or create a service stub. You import these stubs into your project. I mean, this is the import thing. And then you implement a greet service over there. It's fairly simple. There's a greet service that has a greet. It has a call and callback, and you get the name from the call, and then you pass what the return value is going to be. Okay. Then run the service. There are a bunch of things you need to do: register, set the port, and then run the service. Server.start. Okay. Then the client just needs to connect to something that the service runs on. Okay. And call the service with a greet, which says, call the service, check the response. If it is an error, do something. Otherwise, just print the response. Okay. So that's basic thing about how gRPC works. So it's an RPC mechanism for doing that. Okay. There are pros and cons again for this. One is the pros are gRPC supported across all major languages. It's not just TypeScript. So if you write your definition in gRPC, you can actually compile steps for multiple languages and use them. Okay. It is a mature library and there is a lot of community. It is part of the cloud native foundation. So there is a big community and a standard committee working on it. Okay. It's battle tested. It's used at Google, Facebook, all the other places. And it has support for complex data types and all of that. So it solves a lot of problems. But again, there are cons. It's bloated. You must have seen from the code. There's a bit of stuff going on over there to get things working. It's a binary format. That means the good thing about why people choose JSON is that you can spin up a Postman and then hit the API and see what's happening, right? Now, you can do that with gRPC, but you need specific tooling supports and specific tools to do that, okay? The next problem is, like OpenAPI, there is code generation involved. So you still have to generate the code in your compile process to know that something has gone wrong. And it's not idiomatic. When gRPC was first developed, it was targeted Java and Go developers. That's why you see a lot of Java-led patterns in TypeScript over there. So it's not idiomatic, okay? So, but that kind of set the trend for using RPC instead of REST. So there are options. First of them in the RPC framework is Connect, which is an alternative to it's not an alternative to gRPC. It is something that works on gRPC definitions and gRPC tools and all of that. And it's much simpler. Again, you have to generate the stubs. You have to import the type and the router from the generated stubs. And you just implement your service and make it return. So this is as close as we can get to how the ideal scenario that we talked about. Okay. Once you implement the service, the client is quite simple. You say, okay, this is the URL, all of that, and then you create a client saying that this is the type of the client, and that's it. You can call the method, and it is close now. Yeah. 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 So it's always been our experience with gRPC also. So this is much better. And this is the team that was there in gRPC who kind of figured out, we need to change things, make things idiomatic. So now Connect is open, it's production ready. It's a part of, a standard organization. Like, they have it's also a part of the cloud native CNCF. So it is kind of, they have a committee. So it's standardized. So let's look at the pros. It's lightweight, it's idiomatic. There are a lot of tools and services now around Connect. It's part of the CNCF. Uh, the best part is you can switch between binary and JSON also in Connect. So that option is there. It's not just a strictly binary protocol. Plus, there are a lot of services to publish your, interfaces and all of that. Okay, cool. Cons, there's still code generation involved. And again, it's not on real time. Even though a lot of the syntax, everything has been fixed, you still, when something changes, you still need to generate the stubs to figure out that there's a problem in your code. Okay, so it's not exactly real time. You have to, change something, build, and then know something is. Okay. So any questions or anything so far? Yeah. Yeah. I think it's just the readability. And the other one is JSON, right? If you're using something like TypeScript, there's no serialization, deserialization boilerplate you need to write. You can just consume the JSON directly. Okay, that is only on TypeScript. But if you're using another language, that step is still a problem. Right? That's it. What I mean of JSON. I mean, I would say JSON is like the XML. If you all remember XML, it's the XML phase of APIs. Yeah, it is. But yeah, that's why it's popular. So, you know. Okay, so we can still do better. And that's the other one. It's tRPC. Okay. Uh, so again, this is a very TypeScript native way of implementing RPC. How it works is uh, you define a router. Okay, you define the inputs the router should take. For example, in our case, for a greeting, it needs to take a name. Okay, and then it's normal TypeScript code. Just return whatever you want over there, and there, and then you export only the type of the router. Okay, now this is key over here, right? You don't export the entire router implementation. You only export the type implementation in your project. Okay, now your project can now refer to the type. For example, over here, you can say import type service from the server or the service that you're doing, create a client, and then simply call the client, saying client.greet. It's a type of a query, pass in the input parameter, and it kind of works. Okay, over there. Now, again, obviously, pros and cons. Pros is it's idiomatic, it's TypeScript. You don't deal with anything else. There's no code generation, nothing, right? No code generation happening. It works quite well with front-end libraries. And in many of the projects, what we use is, we have our backend services, and then we have a React kind of front end, which talks to these backend services, right? So it works well in that scenario, okay? Because it's got a lot of adapters and all of that. And it was built with that use case in mind, okay? Internally, it uses JSON RPC, not exactly JSON, but I mean, it wraps it around like a JSON RPC. So that's, it is readable. The tools can work with it quite decently, okay? Cons TypeScript only if you have projects, that have other languages, Maybe you don't like TypeScript, you're a Python fan, you can't, confirm, but uh, use the JSON RPC clients in the other one, and then use it. The console it still uses JSON, unfortunately. Sorry. So, conclusion. The most important thing is, in general, right? Exploit TypeScript. Use the compiler. That's the biggest weapon that you have in your project, at least in TypeScript project. Catch things at compile time. Okay. The thing I've seen about TypeScript is, the best thing about TypeScript, you struggle a lot to write your code. You struggle a lot with the compiler, but when you commit it and push it, things just work, because you kind of deferred that struggle much earlier. Even though the other language allows, like Python, allows you to write code and push it so easily, it'll bomb in production, and then you'll have to kind of work it. It gives you that immediate satisfaction of doing things quick and pushing it, but you kind of spoil your weekends because of that. But TypeScript it flips it, right? You struggle a lot when you write it initially, and then things just work. Okay, so catch errors at compile time, put everything together, try to get your project into a way that things are caught at compile time. Okay, avoid contract tests. Sorry. Use monorepos. So doing all of this, I think I'm not. I didn't. This is not a what do you say, ideal situation. We did all of this in our last project. Okay, and there are a few people over here. I hope I'm speaking for them. We were able to commit directly to. Every change gets deployed to production because there is reasonable guarantee that things are going to work. So most of the things did go to production on merge to the main. The feedback cycle is much faster because of that, right? One is because things were caught at compile time, the feedback cycle is much faster. But when things were deployed to production also, in half an hour, you could fix it too, right? So we were able to shorten the feedback cycle so that when something do actually fail, despite all of this, we can actually issue a fix immediately, right? There is no versioning in the project because everything is caught at compile time. We never had to release a specific version of an API or do things like that. Okay. So that is it. Yeah. That's it, class. Thank you. So, questions, thoughts, tomatoes, eggs, anything. Yeah. 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 Mm. 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 Mhm. 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 Yeah. Yeah. Okay. So the use case you're talking about uh, is when you release an API and it's publicly consumed. Okay. And the use case I showed was for internal apps where there is reasonable control over changing APIs. Okay. But for your case, gRPC, it has versioning built into it for both request and response. So the message is versioned on that. And once you release it, it is by default backward compatible. So in the beginning of the talk, I said, we're going to discuss and figure out what the best option is. My preference is Connect and gRPC because all the things that you're talking about, you just mentioned, is there in gRPC, where you can actually, make changes to the proto file, have it versioned so that all clients are supported. Yeah, yeah, yeah. gRPC has support for that. Yeah.
Weird question.
Mhm.
From this one, talk about RPC,
Mhm.
like you said, lots more than make us think about programming
Yeah.
everything instead of
Mhm.
being on a remote computer. It's a
Yeah.
functional local one. And also from what you said about you didn't want a repository to then, at least if I understood it correctly, got the types and everything only in one place, which makes one change. Where's the benefit for writing this or deploying it in like a service based, like I guess architecture deployment system as opposed to funneling it? It's like where all those microservices like included, but deploying it in a matter of it just you can scale certain aspects up. Like that's the only reason I can understand it. You reckon one portion of like an account service might have more usage come through it, scale the amount of what's serving it. Is that the benefit or are there other benefits? Like I guess deploying this in a microservice.
Deploying it to the microservice.
Yeah.
There's a lot of benefit to microservices. In using this, that's a different talk, a heated debate. But generally, building it. I'm not a microservice proponent. I'm more of seeing how things go and then combining and splitting services and all that. But generally, things are better when they are written as a microservice because you could choose to either work on one small part, deploy something, but in this case you have to deploy everything together because things change anyways, right? But the infrastructure handling, load balancing and all is much easier when you do it in a microservice. This specifically solves the problem that okay, I've chosen, I'm going to write microservices, right? And one biggest pain point is API compatibility between these services. So this kind of solves that problem. So yeah. Yeah, sure.
Reason you need one of them, there are some like the services that are using that busy immediately.
Yeah.
What do you do in situations where like the team is different, they have their own code base, they still need to
So gRPC has a mechanism where you can publish your schema. Okay. Earlier that because Google was using it internally, they shared because they had a monorepo, they had one file which everyone refers to, right? And then it compiles now. So they didn't pay much attention to how the schema file is going to be shared. So that's where Connect comes in. They have put in mechanisms where you can push it like an npm repository where you can publish a schema, and when there are changes it will download the schema. The build tool will download the schema, generate things for you, and then make sure things are fine. So it can work outside
or something that will at least
I don't know how I look with this specs. I have to check. Also, I have to keep looking down. Hello. Okay. My phone gets locked every 2 seconds. Okay. So I'm not able to go to the next slide. It's because my phone is got locked. So we're looking at a presentation where we want to not forget that, as engineers, we solve business problems, and it's not about code and just tech. So I'm going to talk us through a case study of a problem we recently solved. Not quite recent, but yeah. The next 40 minutes, we're stuck with slides prepared by me. That's me, Sudarsan, Balaji. And I have some funny notes here. Let me actually read that. So I'm a solution consultant, which means I solve problems for a living. Not the ones you find on LeetCode, but hopefully easier problems than that. The ones that businesses have. I've been writing code since I was in grade 6, but I didn't know I could actually make money until much later. So eventually, I got into Sahaj, where I've been fortunate enough to be able to solve a lot of kinds of problems, write programming, different languages, like 20 plus. Here's a rough agenda. First, we're going to go over a little bit of context of what it is that I'm talking about. Then we look at, what are we dealing with, as in there's a problem, where are things right now? And then we're going to look at what the challenges were. And then we're going to be like, okay, what do we actually want to solve? And then we figure out what can we focus on. And then we discuss how we discuss trade-offs. And eventually, what did we achieve? And what can we learn from that? And then because I talked about simple, and then I had no slide called What's Simple, people were like, what do you mean simple? Like, I can't make the connection. So I made a new slide that says What's Simple. So hopefully, you can understand that slide at the end. And then it's an open forum. I hope it doesn't take 40 minutes, but it might, depending on my nervousness. So before I forget, like, I have to thank a lot of people. So there are people who helped me with the ideas, helped me with the initial stages of the project. There are people helping us even get this client engagement. Some of them you might recognize, but I couldn't remember some of their last names. So a lot of them definitely at the client side. I just can't mention the client names. So the meat of our talk is going to be around digital frames and programmatic. So just to make sure we all understand what they are. So that's an example of a digital frame. It's basically an ad space that has a digital screen. So the way these ads are played is you schedule a creative to say, hey, at 6 p.m. I want this video to play here. That's kind of what happens. And programmatic is a way to have a real-time on-demand ad showing up there. What that means is I know at 6 p.m. I have a blank space. I have empty space that I can show an ad. So at that point of time, I want to call somebody and be like, do you have an ad to play right now? And they're going to tell me, yeah, I have, or no, I don't have. So I'm going to play an ad depending on whether there are ads available at that point in time by calling some people. So that's basically what we're trying to do. Right? So we have some advertising partners that have some bids. So bids are like, I want to play this ad, I'm going to pay you this much money because it's a limited space. Maybe I have like 4 people that want to display their ads there. I have only one place. So they're all going to say, I'm going to pay you, 10p or 15p or 10 pounds to play an ad here. And then we get to decide whose ad gets to play there, and then we get to charge them. So that's basically how programmatic works. Any questions? We are going to work closely in this area, so it's very clear. I mean, it has to be really clear before we go forward. So basically, this is what happens. So there's a frame. I'm an engineer, so I have to prove it using some diagrams. These are diagrams. So here's a frame, and this is a thing called a container. And we call it a container because, like I said before, in a frame, which is a space where you display an ad, you typically schedule a creative, right? But a creative is something like a video or something like an image, so it doesn't have to do anything dynamic. But in the case of programmatic, we actually want to do some action, like we want to call somebody and ask, like, what is the latest ad, something like that. So for that, we need some dynamism. So we typically use a HTML creative, and HTML content can also be just some animated GIF or something. You can also embed an image. But here we are going to add some JavaScript that's going to make an ad request. So the request goes from the container to an SSP, which is typically an ad partner. So I might use SSP, but just make sure you understand that they're just a partner who helps us with ads. So they have ads, we have frames. That's kind of the logic. So there's a container that makes a call to the SSP, and the SSP has, just so I avoid copyright violations or trademark issues, there's 3 ads, one from Popsy, one from Coca-Cola, one from Thumbs Down, right? And these ads don't belong to me, they're with the SSP, right? And when the container makes a request to the SSP, we are going to rely on the SSP to give us one of those ads because at a time we can only play one ad in one frame. So we tell the SSP the information about this frame, like what this frame ID is. And we would have already told the SSP about this frame. Like we would have said, this frame imagine this is an ad space. I would have said this frame is actually in Quality Court, in Holborn, in Chancery Lane, and it's in an office space. So there's a lot of information attached to the frame that the SSP already knows about. And when people give ads to the SSP, they will also have these criteria. Like they'll say, I want office goers to look at this, 24 to 35 people to look at this. And then the SSP can decide, oh, because this frame is here, and there are going to be office people, from 6 to 7, I'm going to let you play this ad, right? Something like that. So the SSP gives us one ad back to the container. And it also says what is going to be the cost to play that ad. Like how much am I going to be paying for that ad space? I'm going to pace myself. I'm out of breath. So hopefully you understand what this is. We're going to go forward with this. Yeah? Can everybody give me a yes? Yes. Thanks. So my phone got locked, so. So there are 3 basic parts of conversation between the container and the ad server, right? So I've written them out. It's a lot of text, so I'm going to explain them really quickly. So firstly, the container needs to know, can I play anything? So there has to be some ad, right? And that information is just about, here's an ad you can play and how much it's going to cost. But the ad itself doesn't come in the response because it's media. So for example, imagine you have a 40 MB video. You want to decide whether to play it or not, right? So you don't want to give the 40 MB video back in that request, in that response from the first time. So you basically ask, do I have an ad to play? And then you get some ad data back. Like here's an ad, and this is what we'll pay you. And then the container is going to send another request saying, can I download the ad? So that's like downloading a file, right? And then it downloads the file. And then once it plays the file, the container also sends what we call a POP, or a proof of play. So the container then says, I finished playing this. It has to send some proof. And that proof is going to be unique for playing this content in this container, in this frame, right? And the ad server is going to be like, oh, so I got a proof that you played it. So I'm going to, send it to my invoicing team. So eventually we get to pay, right? So I'm not going to focus on the reconciliation or the money transfer aspect, but more like this is the whole thing that happens. So we ask for an ad, we get an ad back with some money, and then we play it, and then we say we have played it. That's it. All clear? So every SSP or the partner provides their own container file. So there's an SSP A, they have their own container. There's an SSP B, they have their own container, right? I've tried to use color coding, so let me know if it doesn't help. So on a frame, we can schedule two different containers, but at different points in time, right? So I can say 10 to 11 play this container, but 11 to 12 play the other container. So if we have two different partners and we want to get ads from both of them, we typically have to figure out some way to schedule both of them, right? So our client is basically try to create a system where they want to have, they don't want to share time between two different SSPs. So they have an SSP, they have another SSP. We'll call them A and B for the time being. But if they split them by time, they lose some time where they could have played an ad from one of the SSPs. So imagine 10 to 11, I'm playing SSPA's container. So it's going to only try to contact SSPA to get the ads. And 10 to 11, let's say it doesn't have an ad. Maybe the other SSP would have had an ad from time 10 to 11 at that frame. But because nobody contacted that SSP because the container wasn't playing, they would have not been able to play any ads, right? So what they want to do is build a system that's going to be able to talk to all the partners they have at the exact same time and figure out which partner has the most expensive ad that I can play in that time slot, right? So in order to do that, just like the SSPs, we had to write our own container, right? So the clients have basically come up with their own container, which is a different app, entirely different source code from the other two containers. And it's going to call, I mean, everything we talked about earlier, it's going to call their own ad server. So they literally built an ad server. And on the back end, the ad server is going to talk to the ad servers of the independent advertising partners. Does that make sense? Yeah. So this is what they wanted to take live. So they've been building the system. It's a really complex system because they're trying to do a lot of things because the ad partners, they do a lot of things. They need to know, what the cost of this ad is, right? But every partner is probably dealing with just one currency. So for example, one of the partners might be dealing only in US dollars. The other partner might be dealing in euros or pounds, right? But if you are a service that needs to talk to everybody else, you need to understand what the currency conversions are, right? That's just a small thing. There may be different tax rates. There may be different VATs. Every partner might have different processing fees for an ad. Like because you use them, you pay something called the platform fees. So different partners might have different fees. So even if the cost of the ad is the same, you might be making more money if they come from one partner versus the other partner because the fees are different, right? So there's a lot of things that go in. And the ad server here is built up of 13 plus microservices. They have their own databases. They have like Kafka streams. They have Redis streams. They have Mongo. They have Postgres. They have so many things. And all of that is because they need to do all that in order to be an SSP themselves. They need to know what played where, what is the cost, how much they still have to play, right? A lot of things. So in order to make it really scalable, they had built like a lot of microservices that talk to each other via Kafka messaging so that they can support, like hundreds of partners, even though they right now have only two. And they want to be able to go to multiple business units. So right now they're operating only in the UK, but they have businesses in all of Europe. They have like 10 plus countries. So the team basically had built a very scalable system that's going to work for hundreds of thousands of frames and multiple business units and also multiple different partners. That makes sense. And they're trying to take this live. So that's basically the problem that they came to us with. We've been working on the system. It's really complex, but we've almost gotten to the finish line. We've been working on this for like 1.5 to 2 years. We just want to take this live. So that's where the story starts. So we need to look at what are the challenges. Like, can we just take the system live, right? We're going to look at a few challenges. So firstly, we need to talk about a rollout plan. Like there are, again, thousands of frames in just the UK. So even if you want to just roll out this new thing to all of the frames in the UK, we need a plan. Like what happens to what is live today, right? How do we replace that? Because every container that's scheduled today, we have to change to become this new red container, right? So currently there are yellow and blue containers scheduled, A and B, we recall. So the challenge with that is they have to contact the scheduling team in order to schedule this new container that they have. And the scheduling team takes anywhere from 6 to 8 weeks to get that new content scheduled. That's basically their turnaround time. So the reason they have that long turnaround time is because the scheduling team also has other priorities. So they need to look at billing, they need to reconcile the data, they have a lot of financial constraints. So they can't do that really quickly. So the problem is there's a lack of adequate safety. So there's not enough tests, there's not enough process, there's no release plan yet. And there's a high chance of failure because we're changing a lot of things at the same time, right? So literally every function in the container, like playing the media, downloading it, making the add request, and sending the proof, and logging everything, and invoicing, currency exchange, talking to all of the ad providers. Everything is changing at the same time. So it's not really easy to do that without a high chance of failure. So there's another challenge. Like when I was in college, I used to be interested in building robots. And then there was this first robotics event, and I had spent 3 days trying to build a robot. And I had tested it, and I'm just going to take it to the live event. It's like a map that I have to walk through with the robot. It's a pretty simple event. And then I go there, and then it stops working. I'm like, what? I was testing this until now. Right? So I got reminded of this saying my mechatronics professor used to say often, that there's a difference between mechanical and electronics. Does anybody know what the difference is between electronics and mechanical systems? So you can build mechanical robots, like a first tank is a mechanical robot. They are generally, there's a difference between those and electronics-based robots. Anybody has a guess what the difference is? Okay. Anything else? Exactly. So electronic systems are terrible at reliability. So they can break in so many different ways. Generally, mechanical systems are way more reliable. The problem is that electronic components have too many components, too many connections that can fail, and things can go wrong. So that's what we're also trying to avoid. So in this system, because there are so many different microservices, so many different components, they need to talk to each other in order to get things to work. There's multiple points of failures, and even a single component has so many different ways to fail. Like, for example, a Kafka queue may never drain. It can be overloaded. It can be unreachable from another service. And that's just one example, right? But every time we have like different points of failure, that's a challenge. But also taking things to production is not where the end goal is, right? So once things are in production, things may break, and we need to be able to support that system. So there are also challenges there. So in this particular set of 13 microservices, some of them are written in Node, some of them are written in JavaScript. Sorry, some of them are written in Java and JavaScript. So people who are on the team right now, because it's been built over a period of 1.5 to 2 years, right? So the team has been changing over time, not like the same team. And the skill sets have also changed. So people who started some of these services no longer exist there. People who are working on the current services, they're working on a different tech stack compared to the previous ones. So in general, a lot of the people on the current team are not able to support all the services because they don't know the exact same tech stack. So they need to learn a lot more in order to support them. And also, a distributed system is a lot more complex. So when we have like people who have no experience dealing with the distributed system, it's going to be quite complex to deal with. So that's another challenge. We also need to be cautious about the money we burn on projects. So cost is also a consideration. So when we have like 4 environments, 13 services, a lot of databases, the costs are going to quickly keep adding up, right? And you have these live without users, without it going to production for 1.5 to 2 years, it's going to keep racking up cost. So we also want to not do that. It's obviously easier to change one thing, but to change everything at the same time, it's also a problem. So that's also a challenge. Like we are going to change everything at once. We need enough testing to prove that once we change all of them, things are going to work. And because of this, we may be throwing away a lot of working stock. So when we change all the components, we can't reuse anything that we built. So in the diagram I just showed, it was like full blob of thread, full blob of thread. We are not reusing anything that used to exist before, except for the add partner APIs, that we are still going to use them, right? So there's a mountain of challenges with. Oh, thanks for the water. There's a mountain of challenges. Maybe it's time to look at what problem we wanted to solve in the first place. So we can figure out, do we actually go through and solve all these challenges and then take it live? Or could we look at some other problem which is easier to solve, which maybe we can get to production faster with? So we want to understand what we want to solve, what problems kind of exist. So maybe the first problem I'm going to bring up is not going to be the first on your minds. It's not an engineering problem at all. Does anybody want to guess what the first problem we saw was? That's one of the important problems, but not the first one we saw. Yeah, people watch. So yeah, it is related to people. So basically, there's a tech team that wants to enable the business with the latest and greatest tech. They want to do the best job, right? and they want to get something released which uses the best of technology. It's very highly scalable and all that. So that's the first problem, that the team is trying to prove itself. Like there's because they've been working on this for quite some time, the tech team has lost some reputation with the business. The business is like not trusting the tech team to deliver on its terms. So the team is desperately trying to release something in order to get that trust back from the business. So that's the first problem. Then the case of the long feedback loops, we noticed that it's going to take 6 to 8 weeks for them to deploy something. So the challenge is, even if they deploy something and a small part of it is wrong, for them to roll back is going to take 6 to 8 weeks, which means those frames that are loading the container, they're not going to work. They're not going to be generating any revenue for 6 to 8 weeks. That's a really big, expense and a huge risk. So we can't actually also rely on the scheduling teams because they can't prioritize this work. We can't actually force them to prioritize this work because their priorities are even more important because they're looking at finance, getting money from apps that have already been played and stuff like that. So we also have the other problem where we have 2 different partnerships with SSPs. There are 2 different partnerships we have already made and the client has made, and they're trying to basically get the maximum value out of those established partnerships. We probably signed a contract with some hefty fees, and we need to make the maximum money out of this. So having these 2 different container files sharing half the time is not cutting it. That's one of the main reasons they wanted to build this whole system. This can talk to everything at the same time, right? So that I call underutilized partnerships. Because of the timeshare, we're losing some revenue, right? Then we want to get some data on what actually is the loss due to the timeshare. Like for example, how many ads does SSPA have, or how many ads does SSPB have? Unfortunately, we don't have any of the data. So that's another problem we want to solve. We don't have data to drive any decisions. So we want to build a new system, the whole 30 microservices. One of them was heavily into monitoring, creating dashboards, logging everything. That's because they wanted to solve this problem. They want to have data that they can see to understand how does the market perform, how do our partnerships perform, do they give us less money, more money, should they give us more ads, less ads, right? So these are all the problems that we want to solve. What do you think we should focus on next? What's the biggest problem we need to solve before we can solve anything else? Okay, anything else? Making it simple. Okay, I'm talking about these problems. So whatever change we want to make, like whatever we want to take live, it's still affected by the big feedback loop. So that's the first problem to solve. Obviously, Veda knows her shit, so you should listen to her. So we want to solve the long feedback loops problem first. So we can look at what can we focus on. The first thing is to reduce time to production and to have a rollback strategy, so that if things go wrong, you have a way to bring it back. So if you send a new file and it takes 6 to 8 weeks to schedule, and then you figure out that there's something wrong, you send a bug fix, it takes 6 to 8 weeks to schedule the new bug fix, you basically lose the revenue. You don't want to do that. So we also need some data to understand how we can make these choices on what to do in order to do this. So we want to understand this is supposed revenue loss because of the timeshare between SSP A and B. We want to understand what is the impact of the timeshare. So we look at some data on what is the response rate of these 2 partners we have, right? So obviously we can look at some data. So we went back, we look at the data of what have been the response rates. The response rate is basically for 100 requests you make, how many ads did you actually get back? So we looked at this data, right? And we also need to understand how much money is actually in progress, right? I mean, how much money are we losing effectively? So if SSPA, I don't know, an ad might be worth 10 pounds, but with SSPB, an ad might only be worth 1 pound. So they are not equal in terms of money, right? So we are talking about money and not necessarily only response rate. So we also took some data on what the cost or the bid price for these different ads were from the different SSPs for an entire month. So we went back in time and for an entire month we took, and for the last 3 months, we computed the median per month. What is going to be, we basically took the median bid price for every ad and also the median response rates per month, which is calculated per day response rate, but you just accumulate that over 3 months and then say this is the average response rate. So for SSPA, we found that the average response rates were somewhere around 79%, something like that, and the price was about 1 pound, let's say, right? So I'm saying let's say because the exact numbers obviously, but suffice to say that For SSPB, it was the opposite. So the response rate for SSPB was like 16%, but per ad, they were actually bidding for 10 times more than what the other SSP was doing, right? So the next thing we want to do is reduce the blank screens and fix the revenue leak. But now we have some more data to inform us how we can go about doing that, like what should we prioritize on, right? So whatever we do to make these two possible, we need to definitely keep this one in mind, which is make small guarantee changes. So we can't make big bang changes like change everything in one system, change everything in the other system and take it everything to life. That's not possible. We also need to make sure that these changes are well tested. Like if I make a change, I want to make sure that it's tested somewhere so that when it goes to production, I can rely on it, right? So we do have some test players. We should have a way to test them on the test players. So we need a plan to propose any change on what we're going to focus on, because there's already something that's been working on. I mean, that the team's been working on for a while. So we need to present a plan. So we kind of try to come up with a plan, right? So the first thing we want to do is we want to serve the containers dynamically. So what that means is instead of us telling the scheduling team, hey, this is the container you need to put there, we need to start taking control over what container goes to which frame at what time. We can do this because the frames are loading the creative every time. So somehow, if we can get an API call to be made to get what the container should be playing, then we can probably do that. So the first thing we can do is the red things are new, obviously. So we create a new server called the container server, and it has only one job. When the container here, which is a new container, it basically has some configuration saying the partner is B or the partner is A. So what the container server is going to do is going to get information on what this frame is, like the frame ID, like what we heard before, and it's going to get the partner A configuration from the container in the API call. And the container server is going to use the API call to decide if the container says partner A, I'm going to return the yellow one. If it says partner B, I'm going to return the blue one, right? So the very small change, the only change we do is write a new container that literally makes a redirect call into that API. So that API is going to return the actual HTML, and we're not changing anything, functionally, because whatever used to run for that particular frame will always be running the same thing. So whatever we used to say was container A, we basically told the scheduling team, schedule this container, and internally in that container, we set partner A as the config option. So it's like hard-coded value in that container. So we still have two different containers, and the scheduling team is scheduling the two different containers based on where container A should run and B should run. So they still think, there's this 50% time split, and it does exist, but we build a small server which is going to return the right container. So what do we get from this? The next time we want to change something, like we want to change this container A or B, we can do that change without relying on the scheduling team, because we own the container server. We can change the code and say, oh, for this particular frame ID, let's say it's a test frame. I can say only for the test frame ID, instead of serving container B, also serve container A. So 100% of the time, we only call one. We can do that, right? So we have some ability to change, and if things go wrong, we can always revert back. So that's the ability we get. So this is the first thing we want to actually do. So next thing we want to do is proxy the ad request through our servers. So earlier we noticed that container B has rights on which server to call. Like container A will only call ad server A, right? Because it's built by the SSPs, so they want their containers to only call their ad servers. So instead, what we want to do is we want to build a small proxy. So again, Red is basically what we built. So we built a small proxy around container B. Notice that we didn't rewrite a container. Instead, we are just using container B to do the same thing. But we write a small proxy. Whenever it tries to call ad server B, the proxy is going to rewrite that request to call our ad server. So now we are writing a new ad server, and it's just like two different routes. So one is going to say /container, the other one is going to say /ad. So two different endpoints. So it's still a simple server, just has two endpoints. And what is the server going to do? Not much. Whatever the original request was that the container B would have made, the server is just going to pass that through into ad server B. So what we have done is, again, introduce a small touch point where we can control what can happen, but we don't actually control anything. We just say what used to work before is going to still work. But what we have done is taken the power of deciding what server to call away from the container and moved it into our ad server. So now we can make those decisions on the ad server without relying on the container, but we are reusing everything that container B was supposed to do, and we are not, we're just building something small on top. Again, we can test all of this on the test player, right? And if it used to work, it should still continue to work because we're not actually changing much, right? We don't throw away, we build on top of stuff. So the next thing is, how do we actually improve the revenue situation? So we want to overutilize our partnerships, right? So now that we have control over the ad server, we can write some small code here. So instead of passing it through, we're going to make a small change and say, if ad server B returns no ad, contact ad server A. So this is the only case we wrote. I mean, that's the only functional code there because the other thing was just passing through, right? So we just write this small thing here. At least this is the plan. So it's a 3-step plan. First, make the containers dynamic. Second, proxy it to pass through our ad server. Third, just put a condition there. If ad server B doesn't have an ad, send the request to ad server A, right? As far as container B is concerned, it still thinks the ad comes back from ad server B. And the way that happens is the ad server has some code to transform the request and the response into the way, this container is supposed to understand. Does that make sense? Okay. So we are trying to make small changes, and we can again test all of this before it goes to production, before it goes to actual players. And then we can also, because we control which frame gets this, we can control dynamically where to release and when to release. For example, I could say only for this 5 frames, only from 6 to 7 p.m., give this proxy container. All the other time return, container B. I can do that, right? So because I have all the control. So again, notice we are not touching container A at all, because we notice that there's more impact on fixing container B, because only 16% of the time container B gets an ad, right? It's obviously 10 times more, revenue generating, but it has the highest impact where screens are blank. So to bring that down, we are just going to change container B first to just see, proof of concept. I just want to try something really small. But this whole thing, we wanted to take live in like 4 weeks. It's not like going to happen in 2 days. So we're going to give a plan, like we're going to test everything. We're going to roll it out. The first time, scheduling thing is going to take its own time to get it live, right? For the first part. But after that is done, we should be able to push things to production really quickly, right? And after everything, once the containers are being served dynamically, every change we make can directly go to production, because we have a rollback strategy. We can always change some configuration to say for all the frames served, the old files and things like that. It's quick to roll back, so we are able to do that. So, but I also mentioned that we need to start making decisions on data, and that was a problem before, right? So when you want to change approaches like this, how do we actually get data? Like what data do you look at to say is approach 1 better than approach 2? Because we need to make decisions on data. It's not like because I think it's good and it's better than what used to be before, it just goes like, right? I still need to convince people. So here's a small part about how do we talk about trade-offs, right? We still need some data to decide, so we'll focus on that. So this is an example of the data we use to actually decide which approach is better. So A is what is currently in progress, and B is the change we are talking about. This 3-phase plan is going to live, go live 28 days later or 4 weeks. So we are talking about certain considerations like points of failure. What are the number of components involved? What can you, roll out and roll back on day 1? How long is it going to take to build a new feature, to go to a new partner, to expand to a business unit, right? And the self scores are basically scores given by people who are very closely aligned with those solutions or the approaches, so they know what to do, right? They know how long it's going to take on this solution or this approach to be able to add a new partner, to be able to add a new BU, whatever, right? And the importance scores are given by the business. So the business basically got all these priorities, and they're like, they're going to rate how important some of these are. So once you have the importance and you have the self, you can multiply them to create a weighted score. So that's the weighted score. So B has a self and a weighted. Let's just multiply it, right? But you also see some of them are negative and some of them are positive. That means the ones that are negative means the higher it is, the worse it is for the system. So that's why it has a -1 multiplier. And the other things are positive, right? And all we have to do at the end of the day is once business agrees on all the importance metrics, we can just multiply, do a weighted sum and compare which of the scores is better, right? So here is negative, both of them, because most of the things are worse when they are high. So once we have a score, we see that B is the lower one, right? Or actually the higher one, less than negative value is a greater one. So we see that B is clearly better, right? And it's better by 2.5 times, but it doesn't matter because there's little weightage between that, right? So we can use something like this to make sure that it's documented. It's not like a perfect system, but it's something we can all agree on, because nobody who was involved with B actually gave the scores for A. So because A self-scored themselves and B self-scored themselves, they're pretty happy, right? And none of them decided what the importance was. The business did, and the business also had enough data to make an informed choice. So as engineers, it's also on us not only to recommend things, but also understand how do we give people information that's critical to make such decisions, right? And then the decision is always up to the business. Like engineers don't get to decide much, but we do get to decide how to present the data and what data is needed, what do the decision makers need in order to make an informed decision. So it's our duty to inform them. So after we did all this, we decided we'll go with approach B, which is a new thing, the 3-step plan. And what did we get out of that? So when we de-risk and we solve the right problems in small steps, we get some other benefits. So we wanted to make small guarantee changes, and we did get to do that. So we had continuous iterative delivery. So any merge to master was immediately deployed. We had round the clock deployments. We had zero downtime because we had such safe deployment schedules. And we also had a problem of being able to support things in production before, because the team was not well equipped with all the technologies in use, and it was quite a complicated system. So to handle that, we basically had a really tight tech stack. The entire server solution that we had was a single AWS Lambda. It can be completely unit tested because it's a single function, and it's completely functional and stateless. It doesn't depend on any state. The only state it needed was from a SQLite, which is a read-only database. So you don't need a database connection or anything. You just send the SQLite database file along with the Lambda source and read it like a local file, and that's how it works. Because they don't have to write to the database, they are just reading configs, like for this frame, what container should I return, right? And for this frame, what is the ID I should send to the partner? Something very simple like that. It's always read-only. So we can always distribute that across Lambdas. So we can actually have like 10,000 Lambdas running, each one having 10,000 instances of their own SQLite databases, and they don't have to worry about concurrency or anything like that, right? And we only use TypeScript because we have only one Lambda, that's the source. We use one language, one database, and everything that will work in production or after it's deployed will also work in local. So all the logs for us was on CloudWatch. It was very simple to query, so it was pretty simple. We also wanted to build reliable stuff that we can guarantee works, right? So we got that because we had fewer points of failure. There's literally only one way the Lambda can fail, outside of throwing an error that you can't catch. If it throws an error, you can catch it using unit test because it's just a function, right? The only other way it can fail is if it doesn't have access to connecting to the partner APIs. So that's the only way it can fail. So it's fewer points of failure, right? And we have quick feedback loops because we are able to quickly test in our own pipelines using unit tests and everything. The strongly typed code, like Zabil mentioned, we use TypeScript. So we use a lot of type-safe API building design ideas. So we had tested everything, including logs. Like when we wanted to display logs or something, we'll make sure there's a test saying, is this logged when this happens? So that's the level at which we had reliability for that. We also wanted to not cost a lot on our experiments. So when we deploy this Lambda, it costs like 10 pounds a day for supporting 2,500 frames. We had 10,000 concurrency, we didn't need that. We actually spent something like 370 or 80 US dollars a month at that point in time for supporting 2.5K frames. We use the lowest RAM, and because we use a lot of caching when we try to download the container, for example, we saved a lot of data. So earlier versions did not have that problem, but when we introduced this, it's not like we spike the data usage a lot because we use a lot of caching. So what do we get for all these costs? So we actually made 2 times revenue. So this is for every single day. Once we launched this, after those 4 weeks of development, we did this a lot. We never promised any revenue increase, right? We said we are going to reduce the time to production. We're going to work on reducing the number of blank screens, and we're going to reduce the revenue loss. But we actually made 2x revenue. That's more than £1 million over the year. And this is just the day we launched. So after that, we added more frames. We made even more money subsequently, right? We also continue to improve to where they wanted to eventually become, like actually create a competition between these different partners, see which one has the best stack, instead of just doing, fallback B if not A, things like that. But those things eventually happen, right? The first part, we just got this, and we got some immense output out of that. So what can we learn from all this? Any ideas what we can learn from what we just saw? Yes, exactly. So do we actually know what the problem is? When we started off, we thought, is it building the competition engine? Is it taking something live? We don't know what the problem is until we actually try to understand it further, right? So we need to challenge everything. Like many people can be convinced that they know what they're talking about or they know what the problem is. You still need to do the work and figure out what the problem actually is. Like, and then we have this idea of how do we support our arguments? Like when we say something is good, this is what we need to do. Do we have enough data to actually support that argument? Like for example, if we had checked, what the response rate is, and it's 79 plus 16, that doesn't even add up to 100, right? That means there is no scope for competition because there's not enough ads. One of them is giving us ads 79% of the time. The other one is giving us ads 16% of the time. That means you only have ads 95% of the time, not more than 100, right? Which means even if you compete, you're not going to exhaust the ad supply. So does it make sense? So we need to, again, look at data. So follow the data. So even when requirements make sense, try to validate the requirements with data instead of just saying, oh, this is what people want me to do, so I'm going to do it. Try to make sure that we have facts and the data to make sure that happens, right? And the other point is like, did we actually need to build a highly scalable system? Like, could we have done that 2 years later? Like, could we have done something else before? Could a simpler Lambda with just, 2 endpoints have solved some larger problems and made a lot more money? So these are things to think about. So follow your instincts. Like, because microservices are standard, or because databases like Postgres are standard, doesn't mean you need to actually use them. Figure out what is actually fitting the problem the best, and follow your instincts. Like, don't just take other people's word, but also try to apply your own thing to it. So in a team, different people have different perspectives, but you are you because you have your own unique perspective. So you also need to bring that and contribute that to the team instead of just being like, I'm going to do whatever the team says, right? We also need to focus on value generation. So rather than focusing on the solution, you need to think about how do I generate value, right? Obviously, the 30 microservices for everything that they're doing, they generate a lot of value, but how much time do I have to spend and effort do I have to spend in order to realize that value? Is there something else I can do in a shorter span of time or effort to realize a large chunk of that value without having to go through the same thing? It's like the 80-20 thing. Do we actually need that many components? Could we have made things simpler, things like that, right? So again, own the problem, not the tech. A lot of the time, techies get into this problem of, oh, I want to work on this Kafka thing. I want to work on this Mongo, this new database, this PostDB, this collaboration. Try to own the problem, like focus on what the problem is rather than the tech side of things. Then we usually get to better solutions, right? And then the last thing is, do we actually consider how expensive things are? Like every time we build a system, we provision an infrastructure or a component, we actually have to pay a lot of money towards that. When we sign up to build a system for the next 6 months, we also need to factor in the cost of development and maintenance of that system, right? So it's not only like the cost of the services we're using, but also the cost taken to build that service and eventually to maintain that service. Maybe you need 2 systems people or 2 people to just keep on maintaining the service. Just factor in costs. Time for a breather for me. Do you think you can already see what simple is? There's one more slide on what's simple. Did I explain the title or we need the next slide? Is it already clear? Okay. Still, I'm going to make it my take of what's simple, right? So firstly, we need to understand the problem. Anybody can think that they know the problem, but we still need to do the actual work. We need to dig in, and I say sink into the problem, like go neck deep, and you cannot come out unless you actually understand what it is. Right? But we also need to make sure that we make decisions with data. It's very simple that you need to know the problem. It's also very simple that you need to make decisions with data. Right? So it sounds very common sense, right? That nobody had to teach you this. That hey, how can I solve a problem before I know it? Right? So I have to know the problem. That's obviously the first step. That's why it's simple, right? And how can I make decisions without having any data to back them up? That's why that's all the simple. Try to always make decisions with data. Sometimes it's not clear what data you need. Try to figure that out first before you try to make the decision. Sometimes it's not clear how you will get that data. Figure that out, get the data, and then make the decision, right? And then we have like, I just need a breather, sorry. So we got to a solution in 3 parts. Could we have gotten there in 15 steps or just 1 step? We could have, but we actually took the time to break down the problem. Instead of saying we're going to do this, we are still trying to break things down. So breaking things down is also something that's very simple. Problems are generally huge, but you can break them down and try to compose them instead of trying to do more than one thing at a time. So that's the next thing, just doing one thing at a time. That's what makes things really simple. Like first thing we said, we're going to make the containers be served dynamically. So that's solving one problem about the feedback loop. And then we didn't try to solve everything else, right? And then we said, oh, now I'm going to just figure out, can I push the responsibility of what ad server gets called into the server instead of the container making that decision. So one change at a time is what makes things really simple. So another thing to think about is something Zabil also touched upon earlier is like when you want to change something, do you break things? And then all the chaos that causes, right? So the way we dealt with problems like that is to make small additive changes, right? We never changed anything. We never went in and changed container B's code to do something. We wrote something new that works on top of container B to change what service it calls, right? So changes like that I call additive changes. So if you make additive changes which only build on top of things, but you don't change or remove something that already exists, that's an additive change. It usually saves a lot of time and cost and energy because you're not mistakenly breaking something, right? If I don't change something, I definitely am not breaking that, right? And then all of this will also come down to less is usually more, right? If you write less code, there's less chance of bugs. If you make less change, there's less chance of risk. Less number of things to know about to support a system means more people can support it and faster, right? Because they don't need to learn that many things. Less cost means you have more money to do other things. Maybe you get a raise, you save something somewhere. So in general, less is more. So these are all what I thought was, something I can share about today on what is simple. That's me. So now it's an open forum. Thank you.
Now let's look at how clients like change how you without delivering anything, for example, or would you still, like, I guess, are you pretty happy with how everything went?
I think I'm pretty happy with everything went. I'm probably not as happy as other places where I've not been able to do things like that. But I think this is one of the best ways I've tried to solve a problem. Yes, please. Yeah. Yeah. So it's more like we saw that these containers are scheduled, right, on top of the frames. So whatever code is in the container is what governs. The frames themselves don't make any contacts, like they don't make any calls. The containers are written by us or the SSPs, right? So they typically use the JSON kind of communication to APIs, like JSON RPC or JSON REST APIs. That's how they talk. So our clients own the frames, yes, and they have a very long lease on the frames. Yeah. Mhm. So do you just want to know what happens in the industry or specific to programmatic and what we're talking about? In general, most of the displays that we saw, like we are talking about a specific part called out of home, which is once you leave the house, whatever you see outside that's digital, that's out of home. Also classic, but I'm more talking about digital, right? Because in out of home, you don't have like this tracking like we can do on your phone or your laptop. In general, there are certain agencies which take it upon themselves to create, an approximate representation of what people walk through something, what people can see something, and just use those scores. So we say, oh, for every frame, for every time of every day, like 4 p.m.s on Mondays, 4 to 6 p.m.s on Mondays, this is the approximate crowd that walks by and can look at this frame. So they come up with this number after a lot of surveys and a lot of data engineering, and then they come up with these numbers, and everybody in the industry just agrees to follow them. So anybody who advertises also looks at the same things, like the same metrics on the frames, because they know which frames the ads were playing on. And people who book advertisement campaigns also use the same to guarantee those to clients. So they say, oh, you want an ad here targeting these people. I looked at this data and this is what I see. You can also verify, and the other person can also verify. So they kind of agree on that. Yeah, exactly. Yeah. So it again depends on every media owner. So media owners are basically people who own these displays, the frames. Okay, some of them have large number of these frames. Right, it's probably people like JC Deco and there's global the things we see, right? There's like, I think for most of the tube things I see global on the buses. So these are media owners that actually own these frames. So they get to decide. They typically have their own proprietary pricing algorithms, or how they do that. They won't let you or me in on it. But yeah, generally they have some really good business rules on how they can charge those. In programmatic, we don't get to charge. Like I was saying, people bid for the spots and they decide how much the spot is worth just by bidding. So in the programmatic world, we don't have that problem. Yes, we don't decide. We just, it's a demand supply thing. So if more people want to pay more money, then the place is suddenly worth more. Yeah. No. We don't know whether a frame is available or not. So whenever we get a request from the frame, like from the container file, we know we have a space to play. We don't know that beforehand. So what we have is like some configuration data. Like for example, for this frame, what is the dimension of this frame? Like, is it 1920 by 1080? What can I play on this frame? So some of that data is with us because we need to send that data to the partners to say, hey, I want this kind of mat. So for example, in some frames, you can't play video files, even though it's a digital frame, because let's say it's on a road and there's a local law saying you can't play videos on this, right? So some of this data is in the database. So we use that to say, when I request for an ad, I'll supply these parameters saying, this is the resolution and I can't play videos. I can only play static. And then I get a suitable ad from the ad partners. Does that make sense? Yeah. Yeah. I think is hard to say this is what you do or something. It's more like an approach that if you, I think it's a matter of exposure. Like you expose more people to this way of thinking or solving problems, like breaking things down consistently, using data to drive decisions. It's just something that needs to organically be, osmosized by other people. They see more instances, they understand this is the culture, this is the incentivized way to do things, and then they start doing it because they see the advantages of it. I don't think there's any other way. I mean, we can have these talks, but it doesn't convince people. It just exposes them to the idea, and they have to think about it and be like, does it click for me? Do I think it's a good idea? Maybe then they try. Thanks. Yeah. Thanks. Have a nice evening. I think he's going to do that.